Welcome back everyone. In this lecture we will actually see how to construct some new representations from the old ones. So, we will actually start with some general construction like dual of the representations, tensor products and so on. So, let us first recall what is the dual. Okay. So, let us start with some general G modules. Okay. So, let us say G being finite dimensional Lie algebra. So, maybe you can take it to be SLN or GLN, no issue. So, let us take V being a finite dimensional G module. So, then one can actually talk about the dual of V. So, which is just the home space from V to C. So, this is the set of all C linear maps from V to C. Okay. So, this has naturally a vector space structure and the dimension of V is same as V star. So, given a basis of capital V, one can construct the dual basis of this V star. Okay. So, now we are given that V is a finite dimensional G module. So, we want to actually define G action on V star. Okay. How one can define? One can define using this formula. So, given X inside G, okay, for X in G, F in V star and capital V in V, we define X dot V, which is the new element of V star. So, we need to say that how it is defined on capital V. So, X dot V F, which is acting on V to be just minus F of X V. So, we know that already what is X dot V and then we apply F on X dot V with the minus sign. So, this is the action that we define on V star. Okay. So, if you recall to define representation or the module, we need to have many properties. The very first property is that all the linearity and so on. It should be linear in X, linear in F and so on. Okay. So, all those things will be immediate. So, only the non-trivial condition that one need to check that the bracket x y map to x y minus y x, okay, x dot y minus y dot x. So, that is the thing maybe one can verify immediately and then see this gives representation or the module. Okay, let me just verify only that condition because all other conditions are trivial. So, V star is indeed G module. So, like I said, I will only verify this how the commutator acts. So, let us take two element x and y inside G and then F in V star and then V in capital V. So, then we have, if you take bracket x y and then act it on F and then compute it how it acts on some given element V in capital V, then you can see that this is by definition this is minus F of bracket x y acting on V. So, that means this is same as minus F on x acting on y dot V minus y acting on x dot V. Okay. So, then if you just rewrite this, this is going to be exactly equal to y dot x dot V. So, F applied on this minus F of x dot y dot V. Okay. So, this is what one gets. On the other hand, if we just calculate what happens to x dot y dot minus y dot x, which is acting on F, of course, we need to compute what how it acts on given V. So, this is going to be exactly equal to x dot y dot F applied on V minus y dot x dot F applied on V. Okay. So, then if you just think about it, so we have to take first this element and then apply x. So, that means this is going to give you minus y dot F of x dot V. Okay. because this is the order that in which we are going to use. So, we have to apply it like this. So, first we have to apply y, then on this element, and then we have to apply the other. So, that means, so this is going to give you minus, then it becomes plus, then this is going to give you x dot f of y dot v. Then if you apply one more time, then this exactly gives you f of y dot x dot v minus f of x dot y dot v. So, you can see that this is the first term which matches with this first term, this is the second term which matches with this second term. So, that means both sides are equal. Okay. So, that tells you that from this you can easily see that the bracket x y acting on f is same as x dot y dot f minus y dot x dot f. Okay. This formula is true. So, that makes this dual as a representation of G. So, now one can actually prove this easy proportion. Okay. This is indeed immediate. So, as a first thing, so one can construct the dual of the dual. Okay. And one can easily see that it is naturally isomorphic to as a G module capital V. And the second thing is, so using the first one can prove that if V is irreducible, G module, then one can immediately conclude that V star is also irreducible, G module. So, now using one, it is enough to prove that, for example, V star irreducible implies V is irreducible. Okay. So, let us check both the things. So, if we take for example, this first isomorphism, then how it is actually proved. So, you can actually easily construct this natural map from V to V star of star. So, how one can actually construct? This is actually called evolution. So, let us call it EV. So, given V, so we are going to actually send it to EVV, which is a map from V star to C. What it is? You take some f and then send it to f of v. So, basically given a functional, you just evaluate at v. So, that is what this evaluation map does. Okay. Then it is easy to see that this evaluation map is indeed 1 to 1, because dimension of v is same as dimension of v star. That would imply that this map is indeed vector space isomorphism. So, it is enough to check this map is indeed giving you that modular isomorphism. So, modular isomorphism is again very easy to check. So, let us check that. So, if we take for example, this map as EV, then we need to check EV applied on x dot V should be same as x dot EV applied on V. Okay. But what does it mean in terms of the maps? Okay. So, EV applied on x dot V. So, you are going to apply it on, let us say, some G, okay, for G in V star. So, we want to apply it. Then by definition, so evaluation V map to evaluation at V only. So, that means this is going to be exactly G of x dot V. Okay. On the other hand, what you get it if you apply x dot EV of V on G. So, that is going to be exactly equal to, first you want to see that how this x dot F is defined. Okay. So, because this is in the dual, so this is exactly is going to give us minus evaluation V, which is applied on x dot G. So, this is exactly going to be minus. So, because this is evaluation at V, so x dot G applied it on V. So, you have to do it twice. So, then x dot G at V is going to give you minus of minus G of x dot V. So, that is exactly g of x dot v. So, basically you have to again use this dual action twice, because you are working in v star star. So, that is why you have to apply twice. So, you are getting the same formula as this. Okay. So, that proves that this natural map that we have, this evolution map from V to V star star is indeed isomorphism. So, now the second statement is immediate. For example, one can prove the converse very easily. To prove the second statement, it is enough to prove that V star irreducible implies V is irreducible. Because for converse we can use this first isomorphism, okay, which says V is isomorphic to V star star. So, that means V star V is irreducible, that is V star star is irreducible implies V star is irreducible. Okay. So, why this is true? Let us start with W, which is G submodule. So, then one can talk about the perpendicular of W inside V star. Okay. One can define this perpendicular. So, this is those functional on V star such that which takes value 0 on this entire subspace, which is a natural subspace one can associate with W inside the dual. Okay. It is basically the complement which is with respect to the dual. So, one can easily see that the dimension of V is same as dimension of W plus dimension of W perp. Okay. It is a basically linear algebra, one can prove this. So, now one can easily prove that this W perp is indeed G submodule. Okay. So, I will leave it to you to check. So, this is the first checking, this is the second checking. W perp is indeed G submodule of V star, and this immediately implies W perp is either capital V star or 0, and this immediately implies that W is either capital V or 0. Okay. So, maybe it is the other way. So, that proves that V is irreducible. Okay. It should be the other way. So, that means by considering this the perp of W, one can easily produce representation inside V star, which more or less captures the dual picture. So, that is why V is irreducible if and only if the dual of V is also irreducible. Okay. So, let us look at other constructions. So, one can actually generalize this dual picture to any home space. Okay. So, let us look at the home space. What is it? Let us say V and W being two finite dimensional G modules. Then one can talk about the C linear maps from V to W. So, this is the set of all C linear maps from V to W. So, then one can actually define natural action on this home V comma W. How one can define? So, let us say for F in home V comma W and V in capital V and X in G. So, we define this X acting on F. So, that means it is an again linear operator from V to W. So, when you evaluate at V, so what is this exactly? This is going to be exactly equal to X dot F of V minus F of X dot V. So, this is what the formula looks like. Okay. So, one can verify that this is indeed gives you G action on this home space. So, that makes the space into G module. Okay. So, that I will leave it as exercise. So, verify that home VW is a G module. Okay. So, it is a very easy thing to do. So, now we can also talk about the tensor, okay, and then we will see some connections between the tensor products and these home spaces. So, here is the tensor products. So, as before, let us say V and W are given 5-dimensional G modules. So, we want to construct the tensor product. Okay. So, the tensor product as a space, it is a span of all these simple tensors V tensor W, where V is in capital V and W in capital W. Okay. So, now if you have a basis of capital V, let us say the basis is given by V 1 etcetera V n of capital V, and then you have another basis W 1 etcetera W m of W, then using these two bases one can construct this tensor basis V I tensor W j, where again I runs over 1 to n and j runs over 1 to m. So, this will form a basis of V tensor W. Okay. So, one can define G action on V tensor W and then make V tensor W as a G module. Okay. Indeed, any element of G acts as a derivation. Okay. If you take x in G, then you can make x act on V tensor W by the derivation. It is x V tensor W plus V tensor x W. So, that is how it acts for any V in V and W in W. So, again one can check that this is indeed gives you G module structure. Okay. Maybe I will verify that important important check that the bracket x y, if you take, it acts as the commutator of that respective action x y. So, let us take the bracket x y, apply it on the simple tensors. It is enough to do the computation on simple tensors, okay, because using the simple tensor you can linearly extend the action to everything, and then the check is same as the finally it will come down to the simple tensors. If you take the bracket x y, if you act it on this, then by definition you get it is exactly the bracket x y act on V tensor W plus V tensor the x y acts on W. So, now if you rewrite using the formula, then you will get exactly x dot y dot V minus y dot x dot V, which is tensor with W plus V tensor again x dot y dot W minus y dot x dot W. So, this is what you get. So, if you group them together, then you get exactly x dot y dot W tensor W plus V tensor x dot y dot W, then minus. So, these terms are added together and then minus y dot x dot V tensor W plus V tensor y dot x dot W. So, these two terms are they are together. So, now what we need to prove? So, this is same as saying that x dot y dot minus y dot x acting on V tensor W. So, this is what we need to prove. So, let us compute this. So, this is exactly going to be x dot y dot V tensor W minus y dot x acting on V tensor W. So, which is going to be exactly equal to, first you apply x, first you apply y and then you apply x. So, this is exactly what you get. So, let me see. Okay, so this is going to be the same order, yv tensor w plus v tensor yw, and then you are applying x dot. So, minus again y dot x v tensor w plus v tensor x w. So, which is same as xy v tensor w plus yv tensor x w plus xv tensor yw plus v tensor x dot y dot w minus y dot xv tensor w minus xv tensor yw minus yv tensor xw minus v tensor y dot xw. So, you can easily see that these terms get cancelled, xv yw xv yw and then yv xw yv xw. So, the remaining terms we can match one by one. So, y dot x dot v tensor w is here, this is the first term and this is the second term v tensor x dot yw, and here is the third term with the minus sign. So, this is the third term with the minus sign and this is the fourth term. So, that tells that these two formulas actually simplifies and then says that these two are equal. Okay. So, the bracket x y v tensor w is same as x dot y minus y dot x acting on v tensor w. So, this tells that this formula is indeed giving you the action of G on the tensor product. There is a very close relationship between the home space and the tensor products. So, let us actually look into that. So, if we take this tensor product of the dual spaces, maybe I will leave it as exercise. So, here is the exercise 1. If we take the dual V star tensor V, then this is naturally isomorphic to the endomorphism of V. Okay. The endomorphism of V as a C space, so which can be identified as the home V comma V. Okay. So, now we also have G module structure on both sides. V star tensor V is G module, because V is, if you start with V being a G module, then V star has a dual G representation, and similarly the home space also has G module structure. So, then one can ask that this natural map whether it is a G module map. Indeed, it is G module map. One can actually prove that. So, what is this natural map? One can define it on the simple tensor. If you take this F tensor V, then you can define this FV, which is a map from V to V, which actually takes W to just F of W times V. Okay. One can prove that this map is indeed injective, that is immediately one can easily prove this. So, because the dimension matches, they must be isomorphic, and if you trace back the formula, you can easily see that this is indeed gives you G module isomorphism. And one can extend this to any V and W. For example, on the right side it is home V comma V, you can think about home V comma W. Okay. So, if you take home V comma W on the right side, you can see that naturally you can put V star tensor W on the left side and there is this natural C space isomorphism, which is also G modulo isomorphism. Okay, one can check that actually. Again, the map is very similar to this map. Okay. So, I will leave it as exercise to prove this actually. This is just a simple computation. So, now maybe let us look at some examples and then see what one is getting. So, maybe let us focus on SL2 representations. Okay. So, then we can actually see what this general construction mean in the SL2 representation. So, we also have Weil's complete reducibility. So, we can try to actually decompose given module into direct sum of simple modules. Okay. For example, if we take Vm and then if you consider the dual, okay, we have already shown that V is irreducible implies V dual is also irreducible. That means Vm star is irreducible. So, it must be isomorphic to some V of m dash. But if you think about it, if m is the highest weight for V of m star, then the same weights has to appear for the dual as well. Okay. So, in particularly m will be the highest weight for V m star. So, that means, so there is this natural isomorphism between V of m star and V of m. Maybe I will leave it to you to actually write down. Okay. So, write down explicit map in this isomorphism. Okay, I will leave it to you. Now, one can take two irreducible representation again Vm tensor Vn and then actually ask how it actually decomposes into irreducible representation. Since V tensor W is isomorphic to W tensor V, okay, so that is a very simple exercise. So, you can actually have this flip map if we take V tensor W and then you can define this flip map on the tensors V tensor W map to W tensor V. So, this is the flip map and this map is indeed gives you isomorphism of vector spaces between these two spaces. One can prove that this is indeed G module isomorphism. Okay. So, now using this you can see that Vm tensor Vn isomorphic to Vn tensor Vm. So, without loss of generality one can assume that m is greater than or equal to n. Okay. So, now given this data one can prove that Vm tensor Vn that is indeed isomorphic to Vm plus n direct sum Vm plus n minus 2 direct sum etc. direct sum Vm minus n. Okay. So, this is the exact decomposition of irreducible decomposition of this Vm tensor Vm. So, this is very useful decomposition. So, let us actually try to prove this. Okay. This is again very simple computation, it is not that hard. So, but one has to actually just work it out very closely. So, note that we have this string basis for Vn. Okay. So, let us take that basis. So, the string basis of Vm. So, let us call it V0, V1 etc. Vn. So, now sorry Vm. So, what will be the weights or the H weights? So, that will be starting with m and then going down by 2 all the way to minus m. So, these are all the weights for the basis V0, V1 etc. Vm. Now, similarly, we also have the string basis of Vn. So, that is going to be some W0, W1 etc. Wn. Again the respective H weights going to be n, n minus 2 etc. minus n. Okay. So, these are all the weights for the corresponding natural basis. So, then by general theory we know that this Vi tensor Wj. So, this will form a basis for the tensor product Vm tensor Vn, and where I will run over 0 to m and then j run over 0 to n. Okay. So, now let us calculate H action on Vi tensor Wj and then see what happens. So, this is by using the derivation formula, you can see that this is HVi tensor Wj plus Vi tensor HWj. Note that HVi is given by m minus 2i Vi. So, that is how the H acts on the basis Vi. Similarly, HWj is given by n minus 2j Wj. So, these formulas are known. Using those two formulas, we can easily see that this is going to be m minus 2i times Vi Wj plus n minus 2j Vi tensor Wj. That is what we get. If we group them, you get m plus n minus twice I plus j times Vi tensor Wj. So, that is what we get on the basis. So, that means m plus n minus twice I plus j. So, these are all the weights of Vm tensor Vn. Okay. And note that where they lie, they lie inside m plus n minus m plus n. Okay. This is, they lie in this interval, and not only that, so they are the weights that have same parity as m plus n. Okay. The parity of this is same as parity of m plus n. Okay. Note that in that case, so what are all the elements that will have parity same as m plus n? Okay. So, you can go on non-negative integers that you get. Okay. You can start with m plus n and then go all the way to m plus n minus 2 and so on. We can go up to m minus n. So, that is where you will be actually stopping. So, all these numbers will be non-negative and all of them will have same parity as m plus n, because this m minus n is same as m plus n minus 2n. Okay. So, this will have same parity as m plus n. So, if we actually want to actually decompose this Vm tensor Vn as direct sum of irreducible modules, then we have to see what are all the non-negative weights that we are getting from the weights of this Vm tensor Vn, because they may contribute to the irreducible, that highest weight for the irreducibles. Okay. And you can easily see that these are all the only non-negative integers, okay, which has same parity as m. Actually, like okay. So, there could be more numbers, actually more non-negative numbers. So, we are going to say that these are all the only numbers that will contribute to the highest weights of the irreducibles. Okay. So, let us see how one can actually get that. So, here is the main observation. So, this m plus n minus twice I plus j. So, those are all the weights of this V of m tensor V of n, and all the weights of this module, they have same parity as m plus n. So, now using this, if we calculate what will be the dimension of given weight space V of n m tensor V of n whose eighth weight space, let us say. So, what is the property of A? The parity of A and m plus n should be same, have same parity. So, that is the first natural condition, okay, because A should be able to write m plus n minus twice I plus j for some I j. So, that should be the case. So, if you want to calculate, so what will be the dimension of this? So, this is going to be basically, this has to come from one of the basis element. Okay. This Vi tensor Wj is what going to contribute to this weight A, So, that means, so you are going to count the number of pairs I j such that this I should lie between m and j should lie between n. So, not only that, this I plus j should be exactly, this a should be exactly equal to m plus n minus twice I plus j. So, if you rewrite that formula, then you can see that this I plus j should be exactly equal to half times m plus n minus a. Okay. So, this is the only property that we have. So, this you count all the tuples I j, because this is the ordered basis. So, V I should come first and then W j should come next. So, this is the ordered tuple I j such that, so these conditions should be satisfied. So, now you can actually count how many of them are there. So, using this you can actually directly prove this formula. So, let me just write the formula. The dimension of Vm tensor Vn, eighth weight space of that is going to be exactly equal to half times m plus n minus a plus 1 if a is bigger than m minus n, and it is going to be exactly n plus 1 if n minus m is strictly greater than a, which is strictly smaller than m minus n. Okay. And otherwise, it will be half times m plus n plus a plus 1 if a is less than or equal to n minus n. So, depending upon where the a comes from, okay, you can easily see that these numbers what appears in the formula. So, that is actually immediate consequence of this formula. So, which is again like not that hard to prove, this formula. Okay. Okay. So, what one can observe using this? So, using this one can immediately prove the following. So, if you take for example, the number of summands that are isomorphic to Vm, okay, we know that that is exactly equal to the dimension of Vm minus dimension of Vm plus 2. So, this is something we know already. Okay. So, the number of summands that are isomorphic to, let us say, V of m dash, that is exactly equal to dimension of V m dash minus dimension of V m dash plus 2. So, this is already we have observed. Now, using this you can easily see that, for example, let us say take m minus n. Okay. So, the number of summands, okay, that corresponds to like m minus n plus 2k, let us say. Okay. Number of summands that are isomorphic to V of m minus n plus 2k. So, now this k will vary from 0 to maximum m, sorry, n. Okay. So, this k can vary from 0 to n. So, if you take that, then you can actually see this number is going to be exactly equal to. So, let us look at the formula. If a is bigger than m minus n, then this is the formula that we have, half times m plus n minus a plus 1 minus. So, you have this m minus n plus 2k plus 1. So, this is the dimension of V m dash. So, we have to subtract minus again half times m plus n minus m minus n plus, so we have to add one more here, 2k plus 2 plus 1. Then if you just work it out, you can see that this get cancelled, and then this is going to give you 2n. So, 2 times n plus k divided by 2 plus 1. So, which is going to give you exactly n plus k plus 1, and similarly here this m and m gets cancelled, then you get 2n and then 2 times k n plus k plus 1. So, it is going to give you minus n plus k plus 1. So, this is again going to be minus, this is, so then you get one more plus 1 here. Sorry, it should be, so this is, yeah, this is minus here, okay. Just let's write it properly. This is going to be 2n and then minus 2k 1 by 2 plus 1. So, it is exactly n minus k plus 1. Here minus, so you get 2n plus twice k plus 1 plus 1, okay, sorry, minus, it should be minus here 1 by 2. So, it gives you exactly n minus k, because this one and that one will get cancelled. So, that means this exactly gives you 1, okay, this difference is just 1. So, the number of summands which are isomorphic to V of m minus n plus 2k is exactly 1, okay. And you can easily prove that, so there will not be any other contribution from the lower terms, okay, which actually comes from m minus 1. So, this is already tells you that from this computation V of m minus n direct sum etc. direct sum V of m plus n sits inside Vm tensor Vn. So, this is something we already proved using this computation. So, now it is easy to see that both the dimension matches, okay. So, indeed you no need to compute anything else, because the both the dimension matches. So, this should be the decomposition of V m tensor V of n into irreducible modules. So, there is no extra terms. So, let us do one small example, okay, and then I will demonstrate this again. So, let us look at V3 tensor V2 and then see actually what happens. So, one can actually see that one can draw this a nice picture. So, this has 4 dimension, this has 3 dimension. So, let us say W0, W1, W2. This is V0, V1, V2, V3. So, then the tensor product actually lies here, okay. So, this is the tensor product, let us put dots there. So, this corresponds to 3, this is 1, this is minus 1, this is minus 3, this corresponds to 2, 0, minus 2. So, now if we consider this diagonal terms, okay. So, all of them will have same weight. So, if I take for example, this particular diagonal term, so then you can calculate the weight. So, it will be 2 minus 3, sorry 2 minus 1, 1, and similarly this is 0 plus 1, 1, and this is minus 2, 3, this is 1. And what will be the weight here? The weight of this is 5, weight of this is actually 3. Similarly, the weight is 3. So, like that you can calculate. So, now you can see that if you call this is capital V, V5, the dimension is just 1. And then, so this is plus or minus 5. Okay. The dimension of V3, again plus or minus, you can see this is 2. So, if you take the dimension of V plus or minus 1, that is exactly 3. Okay, because there is a symmetric and then you are having this. So, now if I take 5, so 5 is going to contribute to the V5. But what is the dimension of V5? The dimension of V5 is exactly 6. Okay. So, the dimension of this is 6 and this is going to give you 5, 3, 1, minus 1, minus 3, minus 5. So, these weights will come from this. Okay. So, already 6 dimension gone. So, if you take it out this one space, that will corresponds to this V5. So, then if you go to V3, then how many V3 can be possible? There is only 2 dimension in the height in the 3 weight space of V. So, one is already taken care by this V5 copy. So, only one remains. So, this can have only one multiplicity. Okay. And similarly, if you go to V1, so V1 again V of 1. So, one multiplicity is taken by this copy of V5 and then one multiplicity is taken by copy of this V3. So, there is only one remains, the dimension of the 1th space inside that. So, that will come here. Okay. So, that is what is going to give you one copy of V of 1 here. So, this way actually, like given this data of the weights, one can immediately write down the decomposition of this capital V into direct sum of irreducibles. Okay. So, maybe you should do some more examples and then be comfortable with SL2 representation theory, because that is what going to help us in order to prove results about the general GLN or SLN modules. Okay, I will stop here. So, we will continue with more representation theory in the next class. Thank you.